Hi there, so this video is on section 7.2 volume, and I'm going to split this lesson into 3 separate videos. So this first video will be on disk method. Before we start talking about disk method for finding the volume of a solid of revolution, let's think back to like geometry, or even when we were studying related rates problems, applied optimization problems, we often had to use volume formulas for three-dimensional objects, right? Like a rectangular prism. There's triangular prisms pictured here, as well as a circular prism, which we refer to as a cylinder. And to find the volume of any of these prisms, if you know how to find the area of the top and bottom, so like if we know the area of the top, which also matches the area of the bottom, we can then just multiply that by the height. And that's going to give us the volume of the three-dimensional object. So unfortunately, not everything is always like that you're trying to find the volume of is not always a really nice shape. Like what if we were trying to find the volume of a loaf of bread? So one idea for finding or estimating the volume of a loaf of bread would be, well, what if you cut it into a bunch of slices, right? Because this is a really irregular shape. What if you cut it into a bunch of slices and then found the volume of each slice? Like if you were able to figure out what the area of the front of each slice was, and then you could multiply it by the width of each slice, and then that would represent the volume of each slice, and then you could add all those volumes up. This should sound familiar, right? Remember when we were first estimating the area underneath a curve, we used rectangles, and we thought about adding up the areas of rectangles in order to estimate the area under the curve. And then we talked about, well, if we use skinnier and skinnier rectangles, or more and more rectangles, infinitely many rectangles, then that estimate got closer and closer to what the actual area under the curve was. And that was the idea behind Riemann sums. So the same idea here, if we were to think about taking thinner and thinner slices of bread and finding the volume of each of those slices, and then thinking about adding all those infinitely many slices up, that would give us the actual volume of the loaf of bread. Now, again, back to the Riemann sum idea. So like this looks like a pretty thick slice, and we'll say it's a width of delta x. If we think about making the width of delta x smaller and smaller and smaller, then that's when we rename it dx, right? When that slice becomes infinitely skinny, just like with the idea of the infinitely skinny rectangles. Now, one issue that we would run into is that if we took a slice out of the loaf of bread, the area of the front wouldn't necessarily match the area of the back. But if we do think about the slices becoming infinitely thin, then we could try and come up with some rule to represent the area of the front and the back of the slice, or we could just use one rule that would represent, because the slice would be so thin, and then adding all those up would give us the value of the volume. So this is the idea behind how we can calculate volume of a solid. So if you know that solid, or you could picture that solid as lying between two values, like think of it as being in the xy plane, where the solid lies between A and B, x equals to A and x equals to B. If the cross section, and cross section I mean slice, so if the slice of the area in the plane is perpendicular to the x-axis, that means that we can come up with some rule for the area in terms of x, where area is a function of x. We'll talk about this more later, but if we were thinking about having horizontal cross sections, so horizontal slices, then we could think about coming up with area as a function of y, and then we would end up integrating with respect to y. But we'll talk about that more later. Now the formulas, the volume formulas that you have come to be familiar with have calculus behind them, or can be derived from calculus. So I think it would be nice for us to start with deriving the volume of a sphere, because this is going to set us up for what we call disk method of calculating the volume of a solid of revolution. Okay, so let's think about being in the XY plane first. So let's think just about having a two-dimensional circle in the XY plane. And that circle has a radius of r. We're in XY plane, has a radius of r. You can see that. So that means that this point here would be r comma 0. This point over here would be negative r comma 0. Okay, so we have this circle. Let me start with a different color actually. Okay, now if we thought about rotating that circle around the x-axis, that would create a sphere, right? Perfectly round sphere. And then if we wanted to think about finding the volume of the sphere, like pretending we don't know that formula, we could go back to the idea with the loaf of bread of like trying to find the volume of the loaf of bread. We could think about taking a slice of the sphere perpendicular to the x-axis. And if I pull that out, I'm just going to focus on this slice, which is really skinny. And if we were to turn this to the front, right, the front of the slice would be a circle with a radius of r. Now going back up here, we do have a cylinder, right, a circular prism. And to find the volume of a circular prism, right, we take the area of the faces and multiply by the height. So if we were to think about finding the volume of one of these slices, which we refer to as the cross section, and this cross section we refer to as a disk. So if we were to think about trying to find the volume of the cross section, let's say that it's a width of dx. That's its width, which is equal to, like if we were using the strategy for the regular prisms, geometric prisms, that would correspond to the height, right? And the radius of this disk, well, that's going to vary, right? Like that's going to be dependent. It's not going to be the radius of the circle that we started with. That's going to be dependent. Let me use a different color here. That's going to be dependent on where we take the slice, right? Like the radius is going to be different depending on where we are taking the cross section in the sphere. This would be r of x, right? So our radius of our cross section is dependent on where we are slicing, on what x value we are taking out a cross section. Well, if we think back to how we started with that circle with a radius of r, the equation for a circle with a radius of r is x squared plus y squared is equal to r squared. And if we were to solve for y, we would get plus or minus the square root of r squared minus x squared. The thing is, couldn't we have generated the sphere by starting with just a half circle? So we could actually think about just even taking the positive square root of r squared minus x squared. And if we're looking at my picture, right, r of x we could say is equal to the square root of r squared minus x squared. And we can also think, well, what if we weren't rotating around the x-axis? What if we were rotating around some other horizontal axis, like y equals to 2? So in order to come up with r of x, it's going to be the point on that curve, which is represented, the y value of the point on that curve, which is represented as the square root of r squared minus x squared, minus 0 for y equals to 0. And I'm just going to start doing that now so that it's not as big of a deal whenever we are rotating around a different axes. So in this picture, this is d of x as well. Okay, so then over here, this is r of x. Which is the radius, corresponds to the radius of this slice. Okay, and if we think back to area of a circle, right, which is the front of the disc, when we're trying to come up with the volume of the disc, that would be equal to the area of the disc, the front of the disc, which is pi r squared, times the height, which the height is dx, the same as dx, right? And the radius in this case, I could probably just, here, I'll leave that as h, and then I'll just rewrite the formula. So in this case, we can replace little r with r of x and square that. And now let's replace h with dx. Okay, so that represents the volume of one slice, of one cross section, one infinitely skinny slice. So then when we're trying to find the volume of the sphere, we can think about adding up those infinitely many volumes of discs. So the volume of the sphere is going to be the integral from negative r to r, going back here, right? If we thought about starting with a half circle or a circle, right? That's from x equals to negative r to x equals to positive r. We're adding up all of those slices. So we're integrating from negative r to r, pi. Now r of x we know is equal to, in this case, the square root of r squared minus x squared minus 0. And you guys know how to integrate this. So pi can get pulled out. And then that just becomes r squared minus x squared. In this case, we would know what little r is, right? Little r, you're integrating from negative r to r. So when we do that, r squared is just going to be treated like a constant. So when we integrate, that'll be r squared times x minus x cubed over 3. And then applying the first fundamental theorem of calculus, that's going to be r squared times r minus r cubed over 3 minus, that's a 3, minus r squared times negative r minus negative r cubed over 3. And then once you've simplified, and you could do the algebra, that ends up simplifying down to something that you should be familiar with, 4/3 pi r cubed, which is the volume, the formula for volume of a sphere. So we're going to use a similar method in order to find the volumes of solids that are rotated around a horizontal or a vertical axis. So anytime the cross sections are perpendicular that you're taking, so the slices that you're taking from a solid are perpendicular to the axis of rotation, those cross sections end up being circles. So if you think about taking a region, might be some oddly shaped region, and rotating it around either a horizontal or a vertical axis, and then think about taking slices, cross sections that are perpendicular to the axis of rotation. Those cross sections will always be those really skinny cylinders, which we refer to as discs. Or you can think about adding up the volumes of those discs, and therefore we end up using the same formula for finding those volumes. So if your cross sections are perpendicular to the x-axis or to some horizontal axis of rotation, if it's not the x-axis, then you are integrating with respect to x, right? So you're integrating from a to b, where a and b are x values, and then your radius of rotation, r of x, is a function of x. So you're coming up with a rule in terms of x and integrating with respect to x. And then if the axis of rotation is vertical, so like the y-axis or x equals to some constant, then you end up taking horizontal slices and integrating with respect to y. So let's do another example. You're going to see we're going to follow the same steps for all of these problems. So we want to find the volume of the solid formed by rotating the region bounded by the x-axis, y equals to the square root of x, and x equals to 1. And coming up with the region that's being rotated is really important. Triple check that you are finding the correct region. So it's not straight. Oops. Try this. Okay, square root of x, so let's say this is 1. Okay, so the square root of x have a point here and here, right? That comes up like this. And then we have a vertical line at x equals to 1. Okay, as well as the x-axis. So this is the region that is going to be rotated around the x-axis. So triple check that you have the correct region that you are thinking about being rotated. Drawing a picture can be a good idea if it's not given to you. Oftentimes on free response questions, the region will be given to you, like a picture of it. And then we are rotating around the x-axis. So that means that we're going to end up taking vertical slices, vertical cross sections, in order to find the volume. So if I thought about rotating this, this would make like a solid dome. Okay, where you could see, if you were to take a cross section, it would be, well, hopefully you can kind of see it. The cross section would be a disc. So our radius of rotation, r of x, would be this, right? So to come up with the radius of rotation, that would be the square root of x minus 0, right? So top minus bottom. Bottom is y equals to 0. Again, I'm just preparing for if we were rotating around a different axis other than the x-axis or y-axis. Okay, so our volume is going to be equal to pi times the integral. We have perpendicular cross sections, right? Perpendicular cross sections here. So that's why we're using washer method. So that means we are integrating with respect to x. It looks like that region is bounded between 0 and 1. We know what r of x is, so we are squaring r of x. And then we're integrating with respect to x. So that ends up being pi times the integral from 0 to 1 of x dx. And then it's just integrating. So x squared over 2 from 0 to 1. And using first fundamental theorem of calculus, that would be 1/2 minus 0. So the volume of that solid is pi over 2. The volume of the solid generated from rotating that region around the x-axis is pi over 2. First step, identify the region. Draw it out. Drawing it out can be really helpful. Or shading it in if it's already shaded in. Then identify what your radius of rotation is. Make sure you understand what you're integrating with respect to, x or y. Vertical slices, you're integrating with respect to x. Horizontal slices, as you'll see, will integrate with respect to y. And then your limits of integration are the x interval that your region is bounded by. So let's do another example. So this is similar, nope, it's not the same region. Similar equations, I meant. But now we're looking at the region that is bounded by y equals to 1. Okay, so let's say that this is y equals to 1. And then we're still using the square root of x. And x equals to 0, which is the y-axis. So this is our region now that's being rotated around the horizontal line y equals to 1. Oops. Okay, so rotating around the line y equals to 1. So if we were to think about this being rotated, it would have kind of a pointy top. Our disc cross sections. So r of x, our radius of rotation, would be top minus bottom. R of x in this case would be 1 minus the square root of x. Top minus bottom. To find the radius of any cross section, you would take 1 minus whatever the square root of x is at that x value. Okay, so then to find the volume, it would be pi times the integral from 0 to 1 of r of x, so 1 minus the square root of x squared. And then we can think about multiplying 1 minus the square root of x times 1 minus the square root of x out. We would get 1 minus 2 root x, or 2x to the 1/2 to help us with power rule, plus x. So then integrating ends up being 4/3 x to the 3/2 plus x squared over 2. And applying the first fundamental theorem of calculus, so that's 1 minus 4/3 plus 1/2 minus 0. And that ends up being pi over 6. Okay, this next example, we are thinking about generating a volume from rotating the region bounded by y equals x cubed, y equals to 8, and x equals to 0 about the y-axis. So this is different. Okay, so let's say that this is 8. We have our x-axis, our y-axis. Right, we have, y equals to 8. And, 1, 2, so that's y equals to x cubed. And then bounded by x equals to 0. So that region is here. Okay, and then I'm actually going to I'm going to copy and paste this because we're going to use this for the next example as well. I just want to be prepared. Okay, so we are thinking about rotating around the y-axis. So that means that we are going to have horizontal slices. If we were to think about this region being rotated, right, we'd have horizontal discs as our cross sections. So to come up with our radius of rotation, r of x, it's now going to be, or not r of x, it'll be r of y. So r of y we would find from doing right minus left. Think back to when we were talking about calculating area under a curve, right? So it would be right minus left. Thing is, this equation is not in terms of y. We need x equals. So that would be x equals to the cube root of y. So r of y can be written as right minus left, cube root of y minus 0, right? Minus x equals to 0. So volume will be pi times the integral. We're integrating with respect to y. So thinking this bounded region, y values, so bottom to top would be 0 to 8. I've already defined what r of y is. dy. Okay, so then that's going to be the integral, pi times the integral from 0 to 8 of y to the 2/3 power, right? When we take this, when we square the cube root of y, which is y to the 1/3 power, dy. So then when we integrate, that'll be 3/5 y to the 5/3. And then when we apply the first fundamental theorem of calculus, that ends up being 96 pi over 5. Okay, and then the next video will pick up here for washer method.